How do you define real? This is a question typically left to the philosophers of the world or the 1999 cult classic film The Matrix. However, physics now has something significant to add to the debate. 3 theoretical physicists, John Clauser, Anton Zeilinger, and Alan Aspect, were jointly awarded the 2022 Nobel Prize in Physics, and this recognition has challenged the status quo by seeking the secrets of the world in the tiniest particles. Their endeavors have proven quantum mechanics are real, and Einstein was wrong. But most importantly, they have evidence the universe is weirder than we thought. Their experiments have laid bare a profound mystery at the heart of reality that the universe is not locally real. Join us today as we dig deep into the groundbreaking experiments overthrowing reality as we know it. One of the most unsettling discoveries in the past half a century is that the universe is not locally real. In this context, real means that objects have definite properties independent of observation. An apple can be red even when no one is looking at it. And local means that objects can be influenced only by their surroundings and that any influence cannot travel faster than light. Investigations at the frontiers of quantum physics have found that these things cannot both be true. Instead, the evidence shows that objects are not influenced solely by their surroundings, and they may also lack definite properties prior to measurement. This is, of course, deeply contrary to our everyday experiences. As Albert Einstein once bemoaned to a friend, "Do you really believe the moon is not there when you are not looking at it?" To adapt a phrase from author Douglas Adams, the demise of local realism has made a lot of people very angry and has been widely regarded as a bad move. Blame for this achievement has now been laid squarely on the shoulders of 3 physicists, John Clauser, Alan Aspect, and Anton Zeilinger. They equally split the 2022 Nobel Prize in Physics for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Colleagues agreed that the trio had it coming, deserving this reckoning for overthrowing reality as we know it. As Sandu Popescu, a quantum physicist at the University of Bristol in England, said, "It was long overdue. Without any doubt, the prize is well deserved." The experiments, beginning with the earliest one of Clauser and continuing along, show that this stuff isn't just philosophical, it's real, and like other real things, potentially useful, says Charles H. Bennett, an eminent quantum researcher at IBM. Each year I thought, "Oh, maybe this is the year," said David Kaiser, a physicist and historian at MIT. In 2022, it really was very emotional and very thrilling, he said. The journey from fringe to favor was a long one. From about 1940 until as late as 1990, studies of so-called quantum foundations were often treated as philosophical at best and crackpottery at worst. Many scientific journals refused to publish papers on the topic, and academic positions indulging such investigations were nearly impossible to come by. In 1985, Popescu's advisor warned him against a PhD in the subject. He said, "Look, if you do that, you will have fun for 5 years, and then you will be jobless," Popescu's advisor said. Today, quantum information science is among the most vibrant subfields in all of physics. It links Einstein's general theory of relativity with quantum mechanics via the still mysterious behavior of black holes. It indicates the design and function of quantum sensors, which are increasingly being used to study everything from earthquakes to dark matter. And it clarifies the often confusing nature of quantum entanglement, a phenomenon that is pivotal to modern material science and that lies at the heart of quantum computing. What even makes a quantum computer quantum? Nicole Younger-Halpern, a National Institute of Standards and Technology physicist, rhetorically asks. One of the most popular answers is entanglement, and the main reason we understand entanglement is the grand work participated in by Bell and these Nobel Prize winners. Without that understanding of entanglement, we probably wouldn't be able to realize quantum computers. But noting that the trouble with quantum mechanics was never that it made the wrong predictions. In fact, the theory described the microscopic world splendidly right from the start when physicists devised it in the opening decades of the 20th century. What Einstein, Boris Podolsky, and Nathan Rosen took issue with, as they explained in their ironic 1935 paper, was the theory's uncomfortable implications for reality, one of which is related to a bizarre quantum phenomenon that we now call quantum entanglement. In the simplest terms, quantum entanglement means that aspects of one particle of an entangled pair depend on aspects of the other particle, no matter how far apart they are or what lies between them. These particles could be, for example, electrons or photons, and an aspect could be the state it is in, such as whether it is spinning in one direction or another. The strange part of quantum entanglement is that when you measure something about one particle in an entanglement pair, you immediately know something about the other particle, even if they are millions of light years apart. This odd connection between the two particles is instantaneous, seemingly breaking a fundamental law of the universe. Albert Einstein famously called the phenomenon spooky action at a distance. This phenomenon, as the name implies, is so strange that even until the 1970s, researchers were still divided over whether quantum entanglement was a real phenomenon or not. And for good reasons. Who would dare contradict the great Einstein, who himself actually doubted it? It took the development of new experimental technology and bold researchers to finally put this mystery to rest. To truly understand the spookiness of quantum entanglement, it is important to first understand quantum superposition. Quantum superposition is the idea that particles exist in multiple states at once. When a measurement is performed, it is as if the particle selects one of the states in the superposition. For example, many particles have an attribute called spin that is measured either as up or down for a given orientation of the analyzer. But until you measure the spin of a particle, it simultaneously exists in a superposition of spin up and spin down. There is a probability attached to each state, and it is possible to predict the average outcome from many measurements. The likelihood of a single measurement being up or down depends on these probabilities, but is itself unpredictable. Though very weird, the mathematics and a vast number of experiments have shown that quantum mechanics correctly describes physical reality. The spookiness of quantum entanglement emerges from the reality of quantum superposition and was clear to the founding fathers of quantum mechanics who developed the theory in the 1920s and 1930s. To create entanglement particles, you essentially break a system into two, where the sum of the parts is known. For example, you can split a particle with spin of 0 into two particles that necessarily will have opposite spins, so that their sum is 0. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper that describes a thought experiment designed to illustrate a seemingly absurdity of quantum entanglement that challenged a fundamental law of the universe. A simplified version of this thought experiment, attributed to David Bohm, considers the decay of a particle called the pi meson. When this particle decays, it produces an electron and a positron that have opposite spin and are moving away from each other. Therefore, if the electron spin is measured to be up, then the measured spin of the positron could only be down, and vice versa. This is true even if the particles are billions of miles apart. This would be fine if the measurement of the electron spin were always up and the measured spin of the positron were always down, but because of quantum mechanics, the spin of each particle is both part up and part down until it is measured. Only when the measurement occurs does the quantum state of the spin collapse into either up or down, instantaneously collapsing the other particle into the opposite spin. This seems to suggest that the particles communicate with each other through some means that moves faster than the speed of light. But according to the laws of physics, nothing can travel faster than the speed of light, right? Surely the measured state of one particle cannot instantaneously determine the state of another particle at the far end of the universe, or can it? Physicists, including Einstein, proposed a number of alternate interpretations of quantum entanglement in the 1930s. They theorized that there was some unknown property, dubbed hidden variables, that determined the state of a particle before measurement. But at the time, physicists did not have the technology nor a definition of a clear measurement that could test whether quantum theory needed to be modified to include hidden variables. It took until the 1960s before there were any clues to an answer. John Bell, a brilliant Irish physicist who did not live to receive the Nobel Prize, devised a scheme to test whether the notion of hidden variables made sense. Bell produced an equation that became known as Bell's inequality that is always correct, and only correct for hidden variable theories, and not always for quantum mechanics. Thus, if Bell's equation was found not to be satisfied in a real-world experiment, local hidden variable theories can be ruled out as an explanation for quantum entanglement. The experiments of the 2022 Nobel laureates, particularly those of Alan Aspect, were the first tests of the Bell inequality. The experiments used entangled photons rather than pairs of an electron and a positron, as in many thought experiments. The results conclusively ruled out the existence of hidden variables, a mysterious attribute that would predetermine the states of entangled particles. Collectively, these and many follow-up experiments have vindicated quantum mechanics. Objects can be correlated over large distances in ways that physics before quantum mechanics cannot explain. Importantly, there is also no conflict with special relativity, which forbids faster-than-light communication. The fact that measurements over vast distances are correlated does not imply that information is transmitted between the particles. Two parties far apart performing measurements on entangled particles cannot use the phenomenon to pass along information faster than the speed of light. Today, physicists continue to research quantum entanglement and investigate potential practical applications. And although quantum mechanics can predict the probability of a measurement with incredible accuracy, many researchers remain skeptical that it provides a complete description of reality. One thing is certain, though, much remains to be said about the mysterious world of quantum mechanics. Indeed. Anyway, one of the first lessons that physicists learned when they started examining subatomic systems in the early 20th century was that we do not live in a deterministic universe. In other words, we cannot precisely predict the outcome of every experiment. For example, if you shoot a beam of electrons through a magnetic field, half of the electrons will curve in one direction while the other half will curve in the opposite direction. While we can build mathematical descriptions of where the electrons go as a group, we cannot say which direction each electron will take until we actually perform the experiment. In quantum mechanics, this is known as superposition. For any experiment that can result in many random outcomes, before we can make a measurement, the system is said to be in a superposition of all possible states simultaneously. When we make a measurement, the system collapses into a single state that we can observe. The tools of quantum mechanics are there to make some sense out of this chaos. Instead of giving precise predictions for how a system will evolve, quantum mechanics tells us how superposition, which represents all the various outcomes again, will evolve. When we make a measurement, quantum mechanics tells us the probabilities of getting one outcome over another. And that's it. Standard quantum mechanics is silent as to how this superposition actually works and how measurement does the job of collapsing the superposition into a single result. If we take this line of thinking to its logical conclusion, then measurement is the most important act in the universe. It transforms fuzzy probabilities into concrete results and changes an exotic quantum system into verifiable results that we can interpret with our senses. But what does that mean for quantum systems when we're not measuring them? What does the universe really look like? Does everything exist but we are simply unaware of it? Or does it not really have a defined state until measurement takes place? Ironically, Erwin Schrödinger, one of the founders of quantum theory, it's his equation that tells us how the superposition will evolve in time, railed against this line of thinking. He developed his famous cat-in-a-box thought experiment, now known as Schrodinger's Cat, to show how ridiculous quantum mechanics actually was. Here's a highly simplified version of cat in a box. Put a cat in a box, preferably live. Also, put in the box some sort of radioactive element that is tied to the release of a poisonous gas. Sorry, it doesn't matter how you do it. The point is to introduce some ingredient of quantum uncertainty into the situation. If you wait a while, you won't know for sure if the element has decayed, so you won't know if the poison has been released, and thus if the cat is alive or dead. In a strict reading of quantum mechanics, the cat is neither alive nor dead at this stage. It exists in a quantum superposition of both alive and dead. Only when we open the box will we know for sure, and it's also the act of opening the box that allows the superposition to collapse and the cat to, suddenly, exist in one state or another. Schrödinger used this argument to express his astonishment that this could be a coherent theory of the universe. Are we really to believe that until we open the box that the cat doesn't really exist? At least in the normal sense, that things are always definitely alive or dead, not both at the same time? To Schrödinger, this was too far, and he quit working on quantum mechanics shortly thereafter. One response to this bizarre state of affairs is to point out that the macroscopic world does not obey quantum mechanics. After all, quantum theory was developed to explain the subatomic world. Before we had experiments that revealed how atoms worked, we had no need for superposition, probabilities, measurement, or anything else quantum-related. We just had normal physics. So it doesn't make sense to apply quantum rules where they don't belong. Niels Bohr, another founder of quantum mechanics, proposed the idea of decoherence to explain why subatomic systems obey quantum mechanics, but macroscopic systems do not. In this view, what we understand as quantum mechanics is true and complete for subatomic systems. In other words, things like superposition really do happen for tiny particles, but something like a cat in a box is most definitely not a subatomic system. The cat is made of trillions of individual particles, all constantly wiggling, colliding, and jostling together. For every time two of these particles bump into each other or interact, we can use quantum mechanics to understand what goes on. But once 1,000 or 1 billion or trillions upon trillions of particles enter the mix, quantum mechanics loses its meaning, or decoheres, and regular macroscopic physics takes its place. In this view, a single electron, but not a cat, in a box can exist in an exotic superposition. However, this story does have limitations. Most important, we have no known mechanism for translating quantum mechanics into macroscopic physics, and we can't point to a specific scale or situation where the switch takes place. So, even though it sounds good on paper, this model of decoherence doesn't have a lot of firm backing, yet. So, does reality exist when we're not looking? The ultimate answer is that it appears to be a matter of interpretation. Well, that's all we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we'll see you next time.